a master's student working with me as well within the context of the VLab project. So, Minh Duc, the floor is yours.
Yes, thank you. So I'll just be sharing my screen. All right, so thank you, GP, for introducing me. I'll be presenting my project, which is a thermodynamic description of important phases for the aluminum industry. So like my colleagues before explained, aluminum is an important metal, and my project focuses more on the impact of impurities in aluminum alloy. This is a challenge facing the industry because as petroleum industries move to other sources of carbon fossils, the quality in the anode grade coke for the aluminum industry has been decreasing with increasing levels of impurities. Here in the figure on the left, you have the vanadium impurity that's been increasing in the anode grade coke since the last few decades. And as well, the blends that are available for the primary aluminum production has increasing contents of vanadium and other impurities. Such impurities are not harmless in the final product of aluminum alloys. And in one study that I showed the results here, you can see that the stress strain curves for a 2000 series alloy, the vanadium content has changed the mechanical properties. And because of the demand for increasing high performance alloys and the need for example recycling, the content in impurities must be tightly controlled. And this leads to my research question, which is what is the impact of chromium, nickel, and vanadium impurities on the production of wrought aluminum alloys, especially regarding the solubility of impurities in beneficial phases, and the formation of new undesirable phases. So my primary objective for my master's project is to improve the existing thermodynamic databases to account for the select impurities. So once again, chromium, nickel, and vanadium in a select aluminum alloy series. So here we targeted the 2000, 5000, 6000, 7000 series. Now these series are interesting because they are high performance alloys used in automotive and aircraft production. We have already identified some of the important phases that we want to look at, seen in this table here. And this whole project has, as applications, we aim for improving the alloy design and alloy elaboration, taking into account the impurities we mentioned. We want to help manage the impact of impurities on the critical phases, and perhaps most importantly in the current climate is the control of impurities in aluminum recycling. Now, aluminum recycling poses its own challenges, most notably the low tolerance of impurities for wrought aluminum alloys compared to cast alloys. And such impurities are difficult to remove. If you look at the three we mentioned, they are much harder to remove compared to, say, magnesium and zinc. And this difficulty and these challenges will affect the whole scrap collection and separation strategy and the whole aluminum cascade recycling plan. Hold on, I have annotation demand from Laura. I don't know if you can just yes. So I'll be continuing. So yes, aluminum recycling is also a key aspect of my project. For the strategy that I'll be using, it's going to be the CALPHAD approach. This is something that I'll also be giving in brief introduction and also an introduction in the FactSage solution module this afternoon. So a bit of self-promotion here. So the CALPHAD approach, if I resume it really quickly, we have to determine systems and phases of interest. So this afternoon, we'll be looking at one particular system, a simple one, the aluminum silicon phase diagram. And from there, we need to collect data from the literature. If such data is not available, we can make our own experiments. We can also use, for our case in the CRCT, we could use atomistic simulations, like we've seen before. After that, we need to choose appropriate thermodynamic models, and one that we developed here at the CRCT is the modified quasi-chemical model. And after that, we can improve the existing database with the goal to test and use the database to make phase diagram coding calculations and to explore the solubility of impurities in phases. So at the beginning of my project, I wanted to look at real alloys and to see which phases are formed. So using FactSage, and once again, this is another example we'll see this afternoon, the use of FactSage for cooling calculations. And also make a note that the calculations I've done here are using a older version of the FT-Lite database, so results may vary. But I started with the 5083 alloy. You can see the composition limits on the table on the left that I pulled from MathWeb. And using the FactSage equilibrium module and selecting the appropriate phases, and I'll cover this in the afternoon on how to select the right phases to ensure that simulation does not last too long. Yes, so doing the cooling calculation, you will be given two options, either the equilibrium cooling or shell Gulliver cooling. Equilibrium cooling, as the name implies, means that the cooling rate is low enough to allow at every point for the phases to interact with each other. On the other hand, the shell Gulliver cooling happens at a fast cooling rate, which means that the phases one form will not interact with the liquid anymore and will be permanently locked in. So running the simulations, we arrive at the results. Here representing the raw data results page. Already from looking at the two cooling simulations, we have some of the phases we previously identified that are present, which is a good sign that our databases are accurate. But also, so we have some other phases that we didn't consider as critical. We looking at the invariant reactions happening during cooling. We can see that the primary phase formed in this case is Al11Cr2, and the Al matrix only occurs later on. And an important thing we can see is the final disappearance of the liquid happens at two different temperatures depending on which mode you're using for the cooling. So here in equilibrium cooling, it happens at approximately 570 degrees Celsius. And for the non-equilibrium cooling, it happens around 430 degrees Celsius. Now, all these results are much easier to visualize if you do a plot. So here you have a comparison between the two modes of cooling, where you can see the final disappearance of liquid being much lower for the non-equilibrium cooling. And you can see, of course, that the main phase precipitated is the L matrix, but at the bottom, you will have the other intermetallic phases. So if we apply a zoom on them, we can see the effect of the cooling rate on the phase formation. So for example, for the both cases, the Al11 CR2 phase is the first to precipitate, because in equilibrium cooling, the phases can interact with each other. The phase is not present at the end of solidification, but in the case of non-equilibrium cooling, because the phases cannot interact with the liquid once they're formed, the composition stays until the very end of solidification. So the study of all the phases for my project is only a small part of the wider VLab study on aluminum phases. Here you can see that we were working on all the series of aluminum. And this is a work in progress. We're working on all aspects of the production process of aluminum alloys. And I'll be contributing also in the part for the recycling of aluminum alloys. To conclude, I want to just show a bit what my current work and what future work I have. So I cannot really overstate the importance of the literature review for the CALPHAD approach. So I need a lot of thermodynamic data from the literature. It's going to be the binary phase diagram data, the ternary phase diagram data, solubilities, activities, enthalpies, heat capacities, and especially ternary phase diagram data. This is something that I'm working right now, and there's still some gaps, as you can see in the table here, that I need to find more information. But once again, this shows the importance of the literature review, because if the data is not there, then we have to use experiments to try and fill in the gaps using EDS, WDS, SEM, and even DSC. And on top of that, I can also help with some heat treatments and mechanical tests in collaboration with our partners. So thank you all for your attention. And I also want to thank our industrial partners for the support. And if you have any questions, I'll be happy to answer them in the chat.
Thank you so much, Minh Duc, for this presentation, which was quite clear. I think we have we have some time for a discussion. So if there's anyone raising their hand, we're up for a discussion. I want to stay on schedule. So what I'll do, while we have a little bit of time on our hand, I will share a schedule for today's meeting, and I will just explain what we'll do this afternoon. So you can see here that in the